The planet cools from glare to glow as an incandescent ocean of rock gives back its heat to space. Iron, already unmoored by gravity, settles inward and gathers as a dense heart, while the silicate mantle above it rolls in broad, slow cells that ferry warmth toward the surface. At the skin of this world, crystals meet and lock, a first hard film that forms, splits, and seals again, like frost that cannot decide whether to cling or melt. Radiative loss is the only road outward, and along that road the earliest crust takes hold. Thin, basaltic, easily pierced by rising melt, yet strong enough to transmit stress from one place to another and to remember it in fractures and fabrics. Beneath, convection continues, a planetary exhale that never truly ends. Above, the crust is new enough to steam. Impacts still arrive, fewer than before but bright and decisive. Each strike lifts and slumps craters, spills shock melts, and rewrites the surface as soon as it is written. Between these edits, the cooling crosses a quiet threshold. Steam condenses, falls as rain, and returns as water that collects in low places to deepen basins and press the lithosphere down like a heavy blanket. The weight of the ocean bends the young plate. The plate answers with elastic flexure and slow flow, a hint of the planet's long habit of balancing loads. Within this scene, a small but durable mineral makes a record. Zircon, dense, hard, indifferent to much of what erases other rocks, grows inside felsic pockets that find momentary space within the mafic crust. Some zircons will later be read as older than 4 billion years, with oxygen isotopes consistent with low temperature alteration, implying liquid water near the surface not long after the first crust takes hold. It is a precise, stubborn detail. The most ancient witness to continents is not a mountain or a slab, but a sand-sized crystal that survives because it resists being changed. Beneath the first skin, the mantle remains hotter than any later age, and that difference appears at the surface in compositions now rare. Lavas rich in magnesium, komatiites, rise in buoyant plumes and spread thinly before chilling to green-black rock, a sign of higher internal temperatures and a steeper thermal gradient between deep interior and vacuum. Heat flux is high. The lithosphere is thin. The gradient stays tall enough to keep circulation moving even when the surface looks still. Out of this mafic plane, lighter patches begin to appear. Tonalite, trondhjemite, granodiorite sweets, the TTGs, buoyant and silica-rich, likely born from the partial melting of hydrated basalt at depth. They do not yet form continents in the modern sense, but they float higher than their surroundings, small rafts that refuse to sink, gathering as nuclei that will matter later. Water works everywhere it can. It infiltrates fractures, lowers melting points, and helps peridotite transform to serpentinite along the infant ocean floor. Hydrothermal fluids circulate through newly made basalt, leaching metals and depositing thin veils of sulfide, while hydrogen freed by serpentinization wanders upward through pores. The chemistry is pedestrian and patient, rock plus water, time plus temperature, gradients relaxing toward balance, yet its consequences are planetary. A quiet irony rests inside this arithmetic. The skin that cools the planet also becomes machinery for moving heat, because water lubricates faults, weakens rocks, and turns thermal differences into motion. Another irony is softer still. In geology, rapid cooling means a few 100 million years, swift enough to be called slow. The accepted fact is broad and sufficient. Differentiation and cooling allow a mechanically competent lithosphere to appear, stiff enough to carry and transmit stress yet weak enough to fail where it must. Iron-bearing minerals align with the early magnetic field as they pass through Kearey temperatures and lock direction on cooling. Isotope systems within zircon and other minerals begin to keep time, uranium to lead, samarium to neodymium, quiet clocks that tick even when oceans boil and crust overturns. None of this asks to be witnessed. Scales change meaning here. The day is too short to measure, the century too brief to remember. A third irony hides in the ledger itself. The first hard skin, made to endure by strength, is preserved mostly in fragments, or erased entirely by the very processes it enables. What persists most clearly is the minute and durable, rather than the grand and obvious. A quiet uncertainty threads the scene, and it remains. Does this first skin behave as a single stagnant lid that wrinkles and overturns from within? Or do fragments already slide and dive as plates, with subduction initiating in some places while others hold fast? Lines of evidence point both ways across the Hadean and Archean. High-pressure metamorphic minerals suggest deep burial and return. TTG chemistries imply melting of hydrated basalt at pressures that may require slabs. Structural patterns in greenstone belts echo vertical flow as much as lateral transport. The timing is debated because the record is spare and reworked. The question is open by degrees rather than by absolutes, and the planet remains unwilling to answer in one voice. At the surface, the choreography stays unhurried. Basalt extrudes along fissures and beneath water cools as pillows that stack like knotted ropes. Ash settles into the sea as thin layers finer than breath. Sediments drift from newborn shores and press older beds, while heat and pressure reorganize minerals into new fabrics. Weather begins its long apprenticeship, teaching rivers to measure distance in ions and wind to learn the patience of dust. The atmosphere, thick with water vapor and carbon dioxide drawn from the interior, scours and softens the skin it touches. Volcanic gases add to the mantle's long conversation with the sky. Magnetized grains cool through their thresholds and hold orientation for futures that do not yet exist. By the end of this interval, the crust is still patchy but firmer, the mantle still hot but less frantic, the ocean real enough to have wind-streaked fetch and tides that test every shore. The planet wears a shell that can crack and heal, relay stresses from one province to another, sprout ridges and accept basins, and carry light rafts of silica-rich rock that refuse to sink. This is not yet the mobile mosaic of later ages, but it is more than glaze. It is a platform with memory. Sunlight lowers through a calmer sky and finds a surface that appears, from a respectful distance, finished. It is not finished. It is ready, which is different. And it only took a few 100 million years to arrive so quickly. The early seas deepen in their basins, the water's weight pressing the lithosphere downward as though the crust itself were a flexible raft bowed by cargo. Above, sunlight catches a shifting skin of waves. Below, the planet's first oceanic crust cools to a uniform basaltic plain that stretches toward every horizon, jointed in hexagonal patterns where it shrank on freezing. The presence of water changes everything. It seeps into cracks, cools magma more quickly, and turns iron-rich minerals to rust. It weathers the basalt's surface to clays that settle in quiet places and thicken the seafloor in layers that do not harden for ages. These clays carry the chemistry of the air and the trace of distant land, and they accumulate in patient bands, each one a faint signal in the dark rock below. The seas mirror the slow drift of the sky, but their greatest mirrors lie far beneath the surface. Dense slabs of basalt reflect seismic waves back toward the mantle, with a clarity that geologists in some later age will learn to read. Salt begins to dissolve from rock and fill the oceans with a taste they will never lose. Hydrothermal vents along ridges and fractures emit plumes of mineral-rich water into the darkness, precipitating chimneys of sulfide that stand like fragile towers until they collapse and rebuild in the same slow cycle. In this heat, chemical gradients are steep and short-lived. Metals drop out of solution in seconds, yet the process itself continues for millions of years without pause. Above the vents, the water cools and falls back, closing the loop. Even without life, this is a system of circulation. One basin, one conveyor of chemistry between rock and water, mantle and crust. The basins themselves are never static. As the crust cools, it contracts and deepens, allowing more water to collect. While far away, a warm swell in the mantle may begin to lift another patch of seabed upward, thinning the lithosphere and hinting at a ridge before any magma breaks through. A quiet irony here. The ocean's deepest places may have once been high ground before the weight of time pushed them below sea level. Another is subtler still. The most stable floor on Earth is the one constantly sinking at its edges, recycled with perfect regularity into the interior. A third sits in plain sight. These oceans are called permanent, yet their shapes will not last. At their edges, the early tectonic rhythm begins to suggest itself. Stresses collect in the crust, not in sudden fits but in long, slow arcs. In some places, heat from below lifts and domes the seafloor until it cracks in parallel faults, while in others, the cooling lithosphere becomes heavy enough to sag, its leading edge dipping beneath a lighter neighbour. Whether these are the first true subduction zones is still a question. The evidence lies in minerals altered by water, at depths unreachable without a conveyor of some kind. Blue amphiboles, high-pressure garnets, and eclogites that return to the surface long after they were buried speak of descent and return, yet the distances and mechanisms remain debated. It is possible that these earliest descents were short-lived, that slabs detached and melted before plunging deep, that the mantle's high temperature made the cycle more vertical than horizontal. Still, the motion was there, stone giving way to stone, heat driving rock downward to be remade. The chemistry of the mantle changes subtly in response. Where oceanic crust descends, it carries water into the mantle wedge above it, lowering melting points and generating new magma. This magma, less dense than its surroundings, rises in small batches, sometimes reaching the surface and building arcs of volcanic rock along the meeting line between two plates. These arcs are rarely straight. They bend in soft curves dictated by the sphere's geometry and the shifting angle of descent beneath them. Over time they will weld to continents or sink back beneath the waves, but here they stand alone, a sign that the floor of the ocean is not fixed. In the broad quiet between ridges and trenches, the abyssal plain grows old. Sediment thickens, temperature falls, and the crust beneath becomes denser as it exchanges atoms with the mantle below. The magnetic field, already reversing on its own timescale, leaves faint striping in the basalt, bands of normal and reversed polarity that march outward from mid-ocean ridges in mirrored pairs, a record written without intention. No one reads it yet. The story will remain buried for hundreds of millions of years. Above, the surface remains deceptively serene. Storms cross without touching what lies beneath. Currents move heat and salt but not rock. A passing comet or asteroid may send waves across the ocean's skin, but the lithosphere ignores them, keeping to its own slower clock. Beneath all of it, convection continues. Hot material rises from depth, cools at the surface, and sinks again in cells thousands of kilometers wide. These cells are not drawn sharply. They blur and shift over geological time, sometimes splitting into smaller circuits or merging into broader streams. It is a planetary current, silent except to the slow language of rock. From the scale of a day, nothing moves. From the scale of 1,000,000 years, continents and basins are already trading places. The uncertainty remains about how close this system is to modern plate tectonics. Some argue that the early crust was too weak to form coherent plates, that it deformed continuously rather than along narrow boundaries. Others see in the preserved rocks the geometry of true plate motion, linear belts of volcanic arcs, paired with opposite-age crust on either side of vanished oceans. The mystery persists because the evidence is filtered through time's selective erasure. Only fragments survive, and those fragments are rewritten by later heat, pressure, and fluid. A quiet analogy offers itself. Reading the early ocean's history is like tracing ripples in ice, long after the water has drained away. And yet, the ocean endures, spreading its weight across the lithosphere, pushing down where it fills and pulling up where it departs. The interplay of load and buoyancy becomes a constant feature of the planet's behavior. Low areas invite water, water deepens them. Deepening changes the balance of forces and invites more motion. In this way, the ocean is both passenger and driver, both the record and the tool of the processes beneath. The surface says nothing of this. A calm horizon hides the bending of stone and the slow tilt of slabs, the rise of ridges and the quiet return of crust into the mantle. Only by waiting far longer than any living witness could endure does the picture resolve. An ocean that changes shape without ever leaving, a crust that moves without seeming to, a planet whose face is a mirror and a mask for the machinery beneath. In the long silence between changes, the seas hold steady, keeping their form just long enough for the illusion of permanence to take root before the next rearrangement begins. The first protocontinent, known to later study as Valbara, gathers from buoyant patches of silica-rich crust that refuse to sink beneath the surrounding basaltic plains, its outline irregular and changing, as small terrains weld together along sutures of ancient mountain belts now worn to low relief. These rafts of tonalite, trondiamite, granodiorite rise above the early seas, shedding sediments into surrounding basins and standing as the earliest persistent highlands on Earth. Though even here the air is heavy with volcanic gases and the sun is weaker than in any later age. The surface of Valbara is a mosaic of volcanic arcs, greenstone belts, and ancient cratons, each preserving minerals that record conditions deep in the crust and high in the atmosphere. Rivers begin to cut across these highlands, slow at first, carrying sand and mud toward the low shelves that rim the protocontinent. Around these margins, tidal flats spread under a shallow sun, building thin layers of silt that trap traces of chemical reactions between the ocean and the air, iron oxides, sulfates, and rare early carbonates. The protocontinent floats on the mantle not as an anchored island but as part of the moving lithosphere, drifting over convection cells that lift one edge and depress another, slowly adjusting its balance. The movement is subtle on any human scale, less than the growth of a fingernail in a year. But over tens of millions of years these drifts become distances that remake maps. In the mantle below, plumes rise sporadically, delivering vast outpourings of lava that bury continental crust under flood basalts, before cooling and cracking to reveal the older rocks beneath. Such intrusions and eruptions add weight in some places, prompting the lithosphere to sag, while elsewhere the removal of dense roots during melting can cause uplift. The result is a landscape that changes both by building and by removing, a slow breathing of stone that does not stop. It is here that the first major fracture lines begin to appear across Valbara's body. Rifts open where mantle heat thins the lithosphere, pulling the crust apart until it drops into elongated valleys, their floors lined with new basalt extruded from narrow fissures. These rift valleys may eventually widen into new ocean basins, their edges retreating as more magma rises to fill the gap. Water floods the low ground, accelerating the transition from valley to sea, and the protocontinent is no longer whole. One quiet irony is that breaking is often the first step toward growth. As rifts open, they create new margins where sediments can accumulate and volcanic arcs can form, adding material to the continental crust over time. Another irony lies in the permanence of impermanence. Svalbard is considered the first great landmass, yet its lifetime as a coherent unit is short compared to the long record of its surviving fragments. A third is that even in this earlier supercontinent cycle, the processes of assembly and breakup are already intertwined, suggesting that stability is always temporary in the architecture of the planet. The geological evidence for Svalbard's existence is drawn from widely separated cratons, Kapval in southern Africa and Pilbara in Western Australia, whose rocks share matching sequences of greenstones and sedimentary layers, similar ages of granitic intrusions, and aligned paleomagnetic records that suggest they once lay together near the equator. These signatures, preserved in minerals that have withstood billions of years of heating, deformation and erosion, form the basis for reconstructing a continent that no one has seen. Yet uncertainties remain. The exact size, shape and duration of Svalbard as a single entity are matters of debate. The paleomagnetic poles are not always consistent. The correlation of rock sequences is sometimes interrupted, and later tectonic overprints blur the original patterns. In this way, the continent exists partly as rock, partly as inference, its image sharpened by evidence and softened by the lack of it. The breakup of Svalbard is driven by the same mantle dynamics that assembled it. Convection cells shift, plumes rise in new places, and subduction zones consume lithosphere along its edges. Where two subduction zones retreat toward each other, the continent between them may stretch and thin until the crust fails, allowing the ocean to intrude. Basins form along these new margins, filled first with volcanic rock, and then with sediments washed from the interior. In the process, the interior of the protocontinent may be uplifted, exposing deep crustal rocks to weathering for the first time, their minerals altering in the open air and feeding chemical signals to the ocean. The separation of fragments does not erase their kinship. Cratons once joined may travel thousands of kilometers apart but still carry matching mineral ages and isotope ratios. These matches will one day allow geologists to trace their paths back through time, to fit them together like pieces of a puzzle that has been scattered and partly worn away. During the breakup, volcanic arcs and accretionary prisms form along active margins, where oceanic crust is driven beneath continental blocks. The heat and pressure of these settings create metamorphic belts studded with garnet, kyanite and amphiboly, minerals that hold pressure-temperature histories in their crystal structures. These belts become sutures when terrains collide, their folded and faulted rocks marking the lines where continents grow. Such additions are often small compared to the whole, yet over hundreds of millions of years they help transform narrow protocontinents into broader, more complex landmasses. The oceans around Svalbard's fragments shift as ridges and trenches migrate. Currents change course, climates adjust, and sediment sources move. The basins left behind by the breakup may become sites of extraordinary preservation, where fine-grained sediments trap chemical signals from the atmosphere and ocean that can still be read billions of years later. Among these signals are the earlier signs of oxygen accumulation, thin bands of iron-rich minerals alternating with chert, deposited as the chemistry of the seawater shifted in response to new inputs from weathering crust and submarine volcanism. The tectonic reorganization that follows the breakup continues for tens of millions of years, with some fragments drifting into new collisions while others remain isolated. Mantle plumes may rise beneath the drifting pieces, adding basalt to their margins or beneath their interiors, altering their density and affecting their stability. Over time, some fragments will merge again, assembling into new configurations that will themselves be temporary. The quiet lesson is that the identity of a continent is less about its boundaries than about the processes that move, join, and separate it. What seems whole is simply a phase in a cycle without a fixed centre. Above all, the story of Vaalbra's breakup is one of motion that is both directional and recursive, of structures that persist in altered forms long after the original has vanished. From the human view, the splitting of a continent is a singular event. From the planet's perspective, it is one turn in an unending rhythm, as familiar as breathing, as slow as stone can be and still be said to move. In this, the first great continent leaves its most enduring legacy, not in its brief unity, but in the fragments that still carry its record, adrift yet connected across the deep floor of time. Beneath the crust, the mantle is never still, its motion shaped by temperature differences that drive slow overturn in vast convection cells, hot material rising in wide columns, while cooler, denser rock sinks toward the core mantle boundary. These currents are not sharp-edged but diffuse, their boundaries blurring and shifting over tens of millions of years, sometimes merging, sometimes splitting, the pattern of their flow as transient as any feature on the surface. Yet their effect on the lithosphere above is decisive. Where mantle material ascends, it expands, lowering density and lifting the overlying crust. Where it sinks, the surface subsides, forming basins that may later become oceans. The process is silent, without vibration. The force spread over areas the size of continents and released on timescales far beyond any perception of change. In a modern analogy, it might be compared to the gentle roll of water in a pan set over low heat, except that here the medium is solid rock behaving plastically, and the cycle may take hundreds of millions of years to complete. Rising mantle feeds the creation of new crust at mid-ocean ridges, where pressure release allows partial melting to generate basaltic magma that seeps upward through fractures. This magma solidifies as it cools, forming new oceanic lithosphere that pushes older crust outward on either side, a conveyor belt powered not by mechanical parts but by buoyancy and gravity. The heat from below also drives hydrothermal circulation, seawater penetrating cracks in the new crust, reacting with the basalt, and returning to the ocean enriched with metals and altered minerals. As the crust moves away from the ridge, it cools and thickens, becoming denser until it eventually meets a subduction zone, where its weight, aided by the pull of its own sinking slab, draws it downward into the mantle. Here, in the downwelling limbs of convection, the oceanic lithosphere is reheated, its minerals changing as they are compressed and hydrated. Water released from the descending slab lowers the melting point of the overlying mantle wedge, generating magma that may rise to form volcanic arcs parallel to the trench. These arcs, often curved to match the geometry of the subduction zone, add new material to the crust and change the composition of the lithosphere they build upon. The feedback is continuous. Upwellings feed ridges, ridges spread crust toward trenches, trenches feed downwellings, and downwellings return material to the depths from which upwellings will one day draw again. A quiet irony rests in the symmetry. Oceanic crust is created and destroyed at roughly the same rate, keeping the planet's surface area constant while the details of its geography never stop shifting. Another irony is that the driver of this cycle is not the slow drift of plates themselves, but the density contrast between hot, buoyant mantle and cool, heavy lithosphere. The surface merely records the consequences. A third is that, Although convection operates on scales unimaginably vast, the mechanism is still the same as that which stirs a pot of soup. There are uncertainties in the details that remain unresolved. How deep the convection cells extend, whether they involve the entire mantle or are layered into separate upper and lower systems, continues to be debated, as do the relative contributions of slab pull, ridge push, and basal drag in driving plate motion. Seismic tomography reveals patterns of hot and cold regions within the mantle, suggesting complex three-dimensional currents, but the snapshots are incomplete, and the long-term evolution of these patterns can only be inferred indirectly. There is also the question of how mantle plumes, those narrow upwellings of anomalously hot rock thought to originate near the core mantle boundary, interact with the broader convection system. Plumes may create volcanic chains far from plate boundaries, as in the case of the Hawaiian Emperor seamounts, yet their role in the overall dynamics of the lithosphere remains a subject of careful investigation. The visible signs of mantle convection are written in the arrangement of ridges, trenches, and volcanic arcs, in the rise and fall of continents, in the widening of oceans and the closure of others. Mid-ocean ridges are the surface expression of upwelling limbs, marked by high heat flow, shallow earthquakes, and a narrow axial valley or volcanic high where lava is extruded. Subduction zones, the surface expression of downwelling limbs, are marked by deep ocean trenches, aligned volcanic chains, and earthquakes that trace the path of the sinking slab to depths exceeding 600 kilometers. Between these boundaries, plates move almost rigidly, carrying continents, oceans, and island arcs as passive passengers on the mantle's slow circulation. The scale is so great that even the tallest mountains are insignificant wrinkles, yet over millions of years the motion is enough to bring continents together into supercontinents and to tear them apart again. The cycle of supercontinent assembly and breakup is itself a product of mantle convection, which organizes plate boundaries into configurations that alternately favor collision and separation. When convection patterns align to push continents together, mountain ranges rise, thickening the crust and altering atmospheric circulation. When they shift to pull continents apart, rift valleys open, volcanic activity increases, and new oceans are born. Over deep time, these cycles influence climate, ocean chemistry, and the distribution of life, even though their pace is invisible within a human lifetime. One quiet analogy captures this hidden power. Mantle convection is the metronome to which the planet's surface dances, but the beat is so slow it can only be heard by listening across epochs. As the convection continues, it reshapes not only the geography but also the thermal structure of the planet. Heat is lost to space through conduction across the lithosphere and advection by rising magmas, gradually cooling the interior and thickening the lithosphere over billions of years. This cooling changes the style of mantle flow, the vigor of convection, and the size and distribution of plates. In the earliest Earth, higher internal heat may have driven more vigorous convection and smaller plates. In the modern Earth, the process is slower, the plates larger, but the fundamental pattern is the same. From above, none of this is visible in the moment. The continents appear to stand still, the oceans to keep their shape. Yet at the scale of hundreds of millions of years, mantle convection is the sculptor of every coast, the architect of every range, the quiet engineer of every basin. The seas shift, the land wanders, and beneath it all the mantle moves, its solid rock flowing at rates measured in centimeters per year, carrying the history of the surface in layers that will never again be seen directly. The stillness of the present is only the pause between motions, the moment when the lithosphere rides the crest of a current that has no shore. Across the vast seafloor, a single, continuous system of mid-ocean ridges winds for more than 60,000 kilometers, an unbroken seam where the planet opens itself to create new crust. These ridges are not jagged mountains in the way of continental ranges, but gentle rises flanked by fault-scarred flanks, their crests marked by narrow valleys or volcanic highs, where molten basalt emerges from the mantle. The process is steady, driven by the upwelling of hot, buoyant material beneath the spreading center. As the mantle ascends, pressure decreases, causing partial melting and generating magma that seeps into fractures. When it reaches the surface, it flows in dark ribbons that chill rapidly in seawater, solidifying into pillow lavas with rounded, blister-like shapes. Each eruption is small by continental standards, but the sum over time is immense, forming kilometers-thick sequences of basalt that drift outward on either side of the ridge. The seafloor nearest the crest is warm, thin, and buoyant. As it moves away, it cools and thickens, subsiding to form the abyssal plains that make up most of the ocean floor. Sediment settles slowly onto this crust, at first just a dusting of fine particles from the water above, then a thicker blanket of mud, clay and shells from the organisms that will one day evolve to inhabit these waters. The geometry of mid-ocean ridges is not fixed. Transform faults offset their segments, creating a pattern of zigzags on the seafloor where plates slide past one another. At these offsets, earthquakes relieve the strain of differential movement, their energy travelling quickly through the surrounding rock. In some regions, ridges are fast spreading, with high magma supply and smoother topography. In others, they spread slowly, producing rugged flanks with deep rift valleys. The differences reflect variations in a mantle temperature, composition, and the rate of plate separation. Above the ridge, hydrothermal vents expel superheated mineral-rich water into the deep ocean. Seawater seeps into cracks, is heated by magma, and reacts with the surrounding rock, dissolving metals and altering minerals before returning to the ocean through chimneys that grow from precipitated sulfides. These vents form ecosystems independent of sunlight, a detail that will be discovered far in the future, but in this age they're only chemical machines, exchanging heat and elements between crust and ocean. The chemistry they drive has long-term consequences, influencing ocean composition and recording in minerals the temperature and chemistry of ancient seawater. The ridge system is the primary site of crustal creation, and its motion defines the kinematics of the plates it separates. As new crust forms, it pushes the older lithosphere outward in both directions, a process called seafloor spreading. The rate of spreading varies from a few centimeters to more than 10 centimeters per year, and these rates, recorded in the width of magnetic stripes on the seafloor, will one day allow reconstructions of plate motions deep into the past. The stripes themselves are the product of the planet's magnetic field, reversing polarity at irregular intervals. As basalt cools, magnetic minerals align with the field at that time, locking in a record that runs parallel to the ridge and mirrors itself on either side. This pattern is one of the clearest pieces of evidence for plate tectonics, though in this age it remains hidden beneath kilometers of ocean. The connection between ridges and trenches is a balance. Crust created at one is eventually consumed at the other. The conveyor-like motion of plates ensures that the total surface area of the planet remains constant, even as the arrangement of continents and oceans shifts endlessly. One quiet irony is that the oldest oceanic crust on Earth today is no older than about 200 million years, an instant compared to the age of the continents, because all earlier crust has been recycled into the mantle. Another is that the largest mountain range on the planet, the mid-ocean ridge system, is also the least seen, hidden entirely beneath the sea. A third is that the ridge both divides and unites. It is the boundary between plates, but also the link in the continuous cycle of crustal renewal. there is uncertainty in the details of how ridges initiate. Did they form in the earlier stages of plate tectonics as narrow zones of upwelling in a stagnant lid? Or did they develop later, when the lithosphere had cooled enough to behave as distinct plates? Modern ridges are clearly sustained by mantle convection, but whether they can form without subduction to balance them is a question rooted in the planet's earliest history. What is certain is that the ridges mark a permanent feature of the tectonic system, zones where the surface is built, not destroyed, where heat from the mantle escapes most directly, and where the lithosphere is at its youngest and thinnest. The structure of a ridge is layered. At the base is the mantle peridotite, partially melted to feed the crust above. Above this lies the lower crust of gabbro, crystallized from magma chambers beneath the ridge. Above that are sheeted dike complexes, the frozen conduits that fed lava to the surface, and at the top the pillow basalts that cool in direct contact with seawater. This layered architecture is consistent across much of the ridge system, forming what is known as the ophiolite sequence when pieces are later thrust onto continents by tectonic forces. These ophiolites, preserved in mountain belts long after the ocean that held them has vanished, will be crucial evidence for the understanding of plate tectonics in the distant future. The ridge also influences the shape of the ocean basin. Heat flow from the upwelling mantle swells the seafloor, creating a broad rise that slopes away from the axis. As the lithosphere cools and thickens with distance from the ridge, it subsides according to a predictable thermal curve, a relationship that can be measured in the depth of the seafloor and used to estimate the age of the crust. This cooling also strengthens the lithosphere, allowing it to carry more load and to eventually sink beneath a neighbouring plate at a subduction zone. In this way, the ridge is the starting point of the lithosphere's life cycle, a place of birth from which every piece of oceanic crust begins its journey toward destruction. The stability of this system is deceptive. The ridge axis may shift laterally, jump to a new location, or even die out entirely if the pattern of mantle convection changes. Triple junctions, where three ridges or ridge fault boundaries meet, can reorganize into new configurations, altering the geometry of entire oceans. Over millions of years, these changes can close some ocean basins while opening others, rearranging the positions of continents and the pathways of currents. Yet despite these changes, the ridges persist in some form, an unbroken network connecting all the plates into a single planetary shell. Above the ridge, the ocean hides its form, but the echo of earthquakes, the heat of vents, and the magnetism of the crust record its presence. It is a quiet frontier without fanfare or finality, yet it is here that the skin of the planet renews itself, cell by cell without pause and without haste. At the far edges of the oceanic plates, where seafloor spreading has carried them thousands of kilometers from their birthplaces at the ridges, the lithosphere is cold, thick, and dense enough to begin its descent back into the mantle. These are the subduction zones, long and narrow arcs on the planet's surface where oceanic crust meets its end, bending downward into deep trenches that mark the interface between sinking and overriding plates. The angle of descent varies, sometimes steep and abrupt, sometimes shallow and sweeping, but in every case gravity is the driver, the dense slab pulled into the mantle by its own weight, dragging the rest of the plate with it. The trench itself is a place of stark geometry, a crescent-shaped wound in the seafloor often more than 10 kilometers deep, with slopes cut by faults and scarps where earthquakes have shifted the ground. Above the descending slab, the overriding plate is deformed, crumpled into accretionary wedges where sediments scraped from the ocean floor are stacked and folded like crumpled paper, forming chaotic ridges that parallel the trench. Farther inland, volcanic arcs rise, fed by magmas generated in the mantle wedge above the subducting plate. This melt is produced when water and other volatiles, carried into the mantle by the sinking slab, lower the melting temperature of the overlying rock. The magma rises slowly, collecting in chambers where it differentiates into a range of compositions, from basalt to andesite to rhyolite, before erupting in a chain of volcanoes whose distribution mirrors the curve of the trench offshore. These volcanic arcs are not merely surface features. They are the visible expression of a deep conveyor that links the crust, the mantle, and the atmosphere in a cycle of constant exchange. The sinking slab itself remains coherent for hundreds of kilometers, generating earthquakes that trace its path into the mantle. These quakes, known as Wadati-Benioff zone earthquakes, occur at depths from the shallow crust down to around 1660 kilometers, the boundary between the upper and lower mantle. The existence of such deep earthquakes is a quiet puzzle. How does brittle failure occur in rock so hot and under such immense pressure that it should deform plastically? The prevailing explanation involves dehydration reactions in the slab's minerals, releasing water that weakens the rock and allows sudden rupture. Still, the details remain uncertain, and the exact role of these reactions in deep focus earthquakes is debated. Subduction zones are zones of both destruction and creation. They consume oceanic lithosphere but also generate continental crust, as volcanic arcs and plutons accrete to the overriding plate. Over time, these additions can grow continents outward, welding new terrains onto their margins and increasing their size. This dual role is one of the quiet ironies of plate tectonics. The same process that erases crust also builds it, and the balance between the two shapes the map of the continents. Another irony is that subduction zones, which appear fixed on human timescales, migrate over millions of years, sometimes retreating toward the ocean they consume in a process called trench rollback. This movement can open back-arc basins behind volcanic arcs, small oceans that may eventually close again when the tectonic pattern shifts. A third irony lies in the lifespan of oceanic crust itself. Subduction is inevitable for almost every piece of it, yet its descent is the very reason Earth's surface is not littered with ancient, stagnant seafloor. In the overriding plate, deformation is common. Compression near the trench uplifts mountain belts, folds strata, and thrusts older rocks over younger ones. These ranges may be short-lived in the geological sense, eroded away as soon as tectonic activity wanes. But during their existence they record the immense forces at play where plates converge. Metamorphism is intense here, with high-pressure, low-temperature rocks like blue schist forming in the subduction complex, carrying mineral assemblages that can only be produced in such unique conditions. These rocks, once exhumed to the surface, serve as markers of past subduction zones long after the trenches have vanished. The sediment budget of subduction zones varies. In some, most sediment is scraped off and accreted to the overriding plate. In others, much of it is carried down with the slab into the mantle, where it contributes to the chemistry of arc magmas. The efficiency of sediment subduction influences the cycling of carbon and other elements between the surface and the deep earth, a process that, over hundreds of millions of years, can alter atmospheric composition. The deep trenches themselves are among the most extreme environments on the planet, with pressures exceeding 1,000 atmospheres and temperatures just above freezing at the seafloor. Yet directly below lies the hot, deforming mantle. These contrasts are sustained by the slow pace of heat transfer through the thick, cold lithosphere of the subducting plate. As the slab sinks, it bends and fractures, allowing fluids to escape and altering its mineralogy through metamorphic reactions. At greater depths, the basalt and gabbro of the oceanic crust transform into eclogite, increasing the slab's density and enhancing its pull into the mantle. This transformation marks a critical threshold in subduction dynamics, making the process self-sustaining once it begins. The presence of subduction zones has profound implications for the planet's thermal and chemical evolution. They are primary sites for the return of surface material to the mantle, recycling not only crust but also sediments, seawater, and atmospheric gases bound in minerals. This recycling helps regulate the composition of the atmosphere and oceans over geological time, contributing to the stability of conditions that allow life to persist. Yet subduction also introduces uncertainties. The exact balance between material returned to the mantle and material added to the crust varies with time and tectonic configuration, and the long-term trends in this balance are difficult to measure directly. Seismic imaging of subduction zones reveals slabs penetrating into the lower mantle in some regions, while in others they appear to stagnate at the 660-kilometre boundary. The reasons for this difference are still debated, involving possible variations in mantle viscosity, composition, and temperature. The global network of subduction zones is not evenly distributed. Most are found in the Pacific Ring of Fire, where the oldest and densest oceanic crust is available to sink. The concentration of subduction here has shaped the geography of the surrounding continents, building ranges like the Andes and island arcs like the Aleutians, while closing ancient oceans such as the Iapetus and the Tethys. Over time, the shifting balance of subduction and spreading will change this distribution, closing some trenches and opening others in different oceans. From the human perspective, subduction zones are often associated with sudden catastrophic events, earthquakes, tsunamis, volcanic eruptions. But on the scale of the planet, these are surface ripples in a slow, continuous exchange between lithosphere and mantle. The true story is one of persistence. Slabs descend, melt rises, arcs grow, sediments are recycled, and the cycle continues without pause. Standing at the edge of a trench, if such a thing could be done, one would see only water, a flat horizon hiding the slope into darkness. But beneath that surface lies a moving boundary, an interface where rock slides into the deep, carrying with it the record of oceans that no longer exist, and making space for oceans that have yet to be born. The continents, riding atop the drifting plates, move with a slowness that defies perception, their paths determined by the deep convection currents of the mantle and the push and pull of spreading ridges and subduction zones. From above, they appear steadfast, fixed against the horizon, yet each year they travel centimetres across the planet's curved surface, closing oceans in some directions and opening them in others. The image most fitting is of ice floes on a pond, immense and self-contained, yet carried subtly by currents beneath. Over millions of years, these small motions accumulate into great migrations, bringing land masses together into supercontinents and then scattering them apart again. The lithosphere beneath the continents is thick and buoyant, composed of ancient cratons with roots that extend deep into the mantle, making them resistant to subduction. Instead, they are shunted sideways when plates converge, colliding with other continents or volcanic arcs, welding together fragments of different origin into larger composite masses. At their margins, where oceanic crust dives beneath them, the continents grow as volcanic arcs and accretionary wedges attach themselves to the edge, adding new rock to the continental crust. Over deep time, these additions can be as significant as the original craton itself, giving continents irregular outlines and varied geology. One quiet irony is that the continents, which seem eternal in human imagination, are patchworks assembled from countless pieces, each with its own origin story. Another is that their most stable parts, the ancient cratons, are often buried beneath younger sediments, hidden from view despite their central role in continental endurance. A third irony lies in their motion. While continents drift across latitudes, their climate zones change, glaciers and deserts alternately covering the same land without altering the land's persistence. The slow convergence and divergence of continents are governed by the geometry of plate boundaries and the arrangement of spreading ridges and subduction zones. When continents approach each other, the ocean between them narrows until its crust is entirely consumed and the opposing continental margins collide. Such collisions are among the most powerful events in the tectonic cycle, thickening the crust and raising vast mountain belts. The Himalaya, formed by the collision of India and Eurasia, is a modern example, but ancient belts like the Appalachians and the Urals preserve the record of earlier unions. These mountains, lofty at their birth, are worn down by weathering and erosion over tens of millions of years, their sediments carried to distant basins. Yet deep within them, metamorphic rocks record the heat and pressure of their making, preserving mineral assemblages that can be read long after the mountains have flattened. Between periods of collision, continents may separate, rifting apart along zones of weakness. Mantle upwelling thins and stretches the lithosphere until it breaks, creating a rift valley that widens into a new ocean. The East African rift today is such a beginning, its faults and volcanic centres marking the slow unzipping of a continent. Over time, the rift will deepen and flood, forming an ocean whose margins will evolve into passive continental shelves. These shelves, broad and submerged, will become repositories for sediments delivered by rivers and currents, preserving thick sequences of rock that record the interplay of sea level, climate, and tectonics. Continental drift also rearranges the planet's climate system. The positions of continents influence the paths of ocean currents and atmospheric circulation, altering the distribution of heat and moisture around the globe. When continents cluster near the poles, ice sheets can grow, increasing Earth's albedo and cooling the climate. When they lie near the equator, warm currents can circulate freely, reducing ice coverage and warming the planet. The rise of the large mountain belts can also shift atmospheric circulation, creating rain shadows and altering regional climates. These changes occur so gradually that they're imperceptible within a human lifetime. Yet over millions of years they can transform deserts into forests and seas into dry basins. The geological record shows repeated cycles of supercontinent formation and breakup, known as the supercontinent cycle. In each cycle, continents are drawn together by the closing of oceans and then dispersed by the opening of new ones. Pangaea, the most recent supercontinent, assembled about 300 million years ago and began to break apart 100 million years later. Before Pangaea there were others, Rodinia, Columbia, Kenoland, each with its own sequence of assembly and dispersal. The causes of these cycles are tied to the large-scale organization of mantle convection, which changes over time as heat is lost from the planet's interior. In the assembly phase, subduction zones encircle a growing supercontinent, drawing in surrounding plates. In the breakup phase, heat builds beneath the insulating mass of the supercontinent, weakening the lithosphere until it rifts apart. The intervals between these cycles are long, hundreds of millions of years, and each leaves a distinct signature in the geological record. Modern continents carry scars from both their assembly and breakup. Ancient sutures where collisions occurred, and passive margins where rifts open to form new oceans. The motion of continents is tracked through paleomagnetic data, preserved in the orientation of magnetic minerals that aligned with Earth's field when rocks formed. These data, combined with geological correlations and fossil distributions, allow reconstructions of past continental positions and motions. Yet uncertainties remain, especially for the earliest parts of Earth's history. where the record is fragmentary and altered. Some cratons have drifted across the globe multiple times, colliding with different neighbours in each cycle, so that their present arrangement is only the latest in a long sequence of configurations. The continents influence not only climate and life, but also the chemistry of the oceans. Rivers carry weathered material from the continents to the sea, delivering nutrients, salts, and dissolved ions. The rate of weathering depends on temperature, rainfall, and the presence of mountain belts, so changes in continental position and elevation can alter ocean chemistry over time. Volcanism at continental margins also contributes elements to the ocean and atmosphere, linking tectonic processes directly to the conditions for life. Despite their mobility, the continents maintain an overall balance of area. New continental crust is generated slowly, primarily at subduction zones, while old crust is rarely destroyed because it is too buoyant to sink. This longevity means that the continents preserve a geological record far older than the ocean basins, with rocks more than 4 billion years old still present in places like Greenland and Western Australia. These ancient rocks, though altered, are fragments of the earliest crust, survivors of a history that has erased all but the smallest portions of the original seafloor. From the human perspective, continental drift is a theory confirmed by multiple lines of evidence, but from the planet's perspective, it is simply the visible surface of mantle convection, a byproduct of the deeper processes that govern its thermal and chemical evolution. The continents are passengers in a cycle they do not control, their routes determined by forces they cannot resist. In their movement lies both the record of Earth's past and the framework for its future. Over the next hundreds of millions of years, their paths will close some oceans and open others, build new mountains and wear down old ones, join distant lands and part familiar neighbours. The stillness we see today is only an instant in their long journey, the pause between one meeting and the next. Gondwana takes shape in the deep past as fragments of earlier continents drift together under the slow pull of converging plates, a vast supercontinent that will one day span from the equator to the polar latitudes. It assembles over tens of millions of years, suturing together cratons and terrains from what are now Africa, South America, Antarctica, Australia, the Indian subcontinent, and the Arabian Peninsula. Along its margins, ancient orogenic belts record the collisions that weld these pieces into a single landmass. Folded and faulted rocks that preserve the heat and pressure of their formation. Granitic intrusions crystallized from the magmas that rose during collision, and metamorphic minerals whose chemistry marks the depth and temperature of their growth. Once united, Gondwana's scale alters global circulation. Its broad interior, far from the moderating influence of the sea, experiences extremes of climate, while its sheer bulk diverts ocean currents into new patterns. At its southern edge, parts of the landmass extend into polar regions, where ice sheets can grow during cooler intervals, sending tongues of glacial ice into the sea and delivering sediment-laden meltwater to continental shelves. Nearer the equator, warm shallow seas flood low-lying margins, supporting reefs and depositing thick carbonate platforms. These deposits will one day be lifted into mountain belts, their marine fossils stranded far above sea level. Gondwana is not a static block. It moves as a single tectonic unit, drifting slowly across the globe, rotating slightly as it interacts with other plates. Subduction zones along its edges consume oceanic crust, feeding volcanic arcs and accreting island chains to its flanks. Some of these arcs weld permanently to the supercontinent, becoming part of its geological fabric. Others are ephemeral, later rifted away when the tectonic pattern changes. The interior of Gondwana is dominated by stable cratonic shields, underlain by thick lithospheric roots that anchor them in the mantle. These shields preserve some of the oldest rocks on Earth, along with sequences of sedimentary basins that record the gradual filling of ancient depressions. Between the shields, mobile belts remain zones of weakness, their complex structures inherited from earlier collisions. These belts can be reactivated when stresses shift, creating new faults and folds or allowing magma to intrude along old fracture zones. A quiet irony is that even the most stable cratons are stitched together from earlier fragments, so the core of the supercontinent is itself a palimpsest of older tectonic events. Another irony lies in Gondwana's stability. It persists for hundreds of millions of years, yet its eventual breakup is already prepared in the arrangement of its internal weaknesses. A third is that while it is remembered as a single unified landmass, most of its story is written at its margins, where interaction with the surrounding oceanic plates is constant. The climate of Gondwana changes over its lifetime, influenced by its position on the globe and by the configuration of surrounding land and sea. During colder intervals, ice sheets spread across its high-latitude regions, scouring the bedrock and leaving behind striations until it will later be preserved in the geological record. These glacial deposits, found today on widely separated continents, are among the key pieces of evidence for the former unity of Gondwana. During warmer periods, large river systems cross its interior, carrying sediments to extensive deltas and shallow marine basins. These rivers carve valleys into the cratons, their courses adjusting to the slow uplift and subsidence of the land. Over millions of years, the sediments they deliver accumulate in layers thousands of meters thick, compacting into sandstone, shale, and limestone. Fossils within these rocks record the evolution of life in the supercontinent's diverse environments, from polar tundras to tropical wetlands. The tectonic forces that assembled Gondwana continued to shape it after its formation. Along its western margin, the subduction of oceanic crust beneath what is now South America builds volcanic arcs and mountain ranges that will one day become the Andes. Along its northern margin, the closure of oceans between Gondwana and smaller continents or island arcs produces belts of high-pressure metamorphic rocks, ophiolites, and complex fault systems. Each of these collisions adds new pieces to the continent and modifies its outline. Yet for all its size and stability, Gondwana is part of the supercontinent cycle, and its eventual breakup is inevitable. Heat builds beneath its thick lithosphere, trapped by the insulating effect of its large area. Mantle plumes may rise beneath it, weakening the crust and initiating rifting. The earlier signs of breakup are subtle: localized uplift, increased volcanism, and the formation of rift valleys along lines of structural weakness. Over time, these rifts lengthen and deepen, filling with lakes and then with arms of the sea as they connect to the ocean. New mid-ocean ridges form, and the fragments of Gondwana begin to drift apart. The breakup will scatter its pieces across the globe, but their shared geological history will remain visible in matching rock sequences, fossil assemblages, and paleomagnetic signatures. One of the uncertainties about Gondwana's history concerns the timing and sequence of its assembly. While the broad outline is clear, details of how individual cratons and terrains joined, and the exact nature of the plate boundaries that brought them together, remain subjects of study. In some cases, the evidence is obscured by later deformation and metamorphism, making it difficult to distinguish between events separated by hundreds of millions of years. Seismic imaging of the crust and mantle beneath former Gondwanan fragments offers some clues, revealing the thick lithospheric roots of cratons and the sutures where they meet. Geochemical analyses of magmatic rocks help to trace the sources of the magmas and the tectonic settings in which they formed. These methods, combined with careful field mapping, gradually refine the picture, though some questions may remain unresolved. Gondwana's role in Earth's history extends beyond its geological structure. Its size and position influenced global ocean circulation, creating barriers and gateways that controlled the flow of currents between ocean basins. Changes in these currents affected climate patterns, nutrient distribution, and the migration of marine life. On land, the unbroken expanse of Gondwana allowed species to disperse widely, leading to shared faunas and floras across regions that are now separated by oceans. This biogeographic legacy is preserved in the fossil record, providing another line of evidence for the continent's former unity. From the planetary perspective, Gondwana is one chapter in the ongoing rearrangement of continents, its assembly and dispersal part of a pattern repeated many times in Earth's history. The present-day positions of its fragments, scattered from pole to pole, are only the latest stage in their long journey. The stillness we perceive in our own time is a momentary pause in the motion that brought them together and will carry them elsewhere. Gondwana's story, like that of every supercontinent, is one of motion without haste, change without end, and a surface that records the slow breathing of the planet beneath. When plates converge, the collision of continents produces some of the most striking and enduring features on the planet. Mountain belts that rise in great arcs, their crests piercing the sky, their roots reaching deep into the crust. These mountains are built by compression, as two buoyant continental lithospheres, neither able to sink, crumple, and thicken where they meet. The process begins long before the continents themselves touch, with the consumption of the oceanic crust between them at a subduction zone. As the trench retreats toward the approaching landmasses, volcanic arcs grow on one or both sides, fed by the melting of the subducted plate. Sediments from the ocean floor and from the eroding arcs are accreted to the overriding plate, forming wedges of folded and faulted strata. When the last of the oceanic crust is consumed, the continental edges collide, and the volcanic arc may be welded to the margin of the other plate. The subduction zone is choked, but the convergence continues, driving the crust upward into a thickened mass. In the deep roots of these young mountains, rocks are buried to great depths, subjected to intense pressures and temperatures. Minerals recrystallize into new assemblages, their chemistry recording the conditions of their metamorphism. Garnet, kyanite, sillimanite, and high-pressure forms of quartz. Partial melting may occur in the lower crust, producing granitic magmas that rise to form plutons, slowly cooling to create the coarse-grained rocks that will one day be exposed at the surface. Faults slice through the thickened crust, accommodating strain in a combination of brittle and ductile deformation. Over millions of years, the rising mountains alter weather patterns, casting rain shadows and redirecting rivers. Their high elevations accelerate erosion as ice, water, and wind work to wear them down. Sediments pour into adjacent basins, building thick sequences that will one day be uplifted in turn. One quiet irony is that the very forces that build mountains also begin their destruction immediately, and the highest peaks are often the youngest in geological terms. Another irony lies in the eventual fate of these ranges. After tens of millions of years, erosion and isostatic rebound will reduce them to rolling hills, yet their deep roots may persist in the crust for billions of years. A third is that mountain belts can record in their structure and mineralogy the precise sequence of events that formed them, even as the surface expression is worn away. The Himalaya offers a modern example, where India's northward motion has driven it into Eurasia, raising the highest peaks on Earth. Beneath the visible summits, seismic studies reveal a crust more than twice the normal continental thickness, underpinned by a deep root of buoyant rock. Faults like the main central thrust record the stacking of crustal slices during collision, while metamorphic zones trace the progressive burial and exhumation of rocks. Ancient mountain belts, such as the Grenville Orogen in North America or the Svekofenian belt in Scandinavia, preserve similar patterns, though their peaks have long since eroded away. In some cases, the rocks at the surface today were once buried tens of kilometers deep, brought back up by exhumation along major fault zones, or by the removal of overlying material through erosion. These rocks may contain inclusions of minerals stable only at great depth, such as coesite or diamond, providing direct evidence of the extreme conditions reached during continental collision. The mechanics of mountain building are tied closely to the rheology of the crust and the forces driving plate motion. The crust thickens not only by direct compression, but also by underthrusting, as one continent is pushed beneath the edge of another without subduction into the mantle. This underthrusting can carry buoyant crust deep enough to undergo high-pressure metamorphism before it is exhumed. At the same time, horizontal shortening can be accommodated by folding, with layers buckling into anticlines and synclines whose wavelengths reflect the thickness and strength of the rock. The resulting structures are often complex, with multiple generations of folding and faulting overprinting one another as the collision evolves. The topography created by mountain building has long-term effects on the landscape and the planet's systems. High elevations capture more precipitation, feeding glaciers that carve valleys and transport sediment to the lowlands. Rivers born in mountain ranges carry dissolved ions and particulate matter to the oceans, influencing marine chemistry and the global carbon cycle. Weathering of silicate minerals in mountain belts draws down atmospheric carbon dioxide over millions of years, contributing to global cooling. In this way, the uplift of mountain ranges can influence climate far beyond their immediate surroundings. Yet uncertainties remain about the balance of processes in orogenesis. The relative importance of crustal shortening versus lower crustal flow, the role of deep-seated detachments in accommodating strain, and the influence of mantle dynamics on the location and longevity of mountain belts are all subjects of active research. Seismic imaging of modern origins reveals that the lower crust and upper mantle beneath mountains are often highly variable in structure, suggesting that each range has its own unique combination of processes. The supercontinent cycle plays a role in determining when and where large-scale mountain building occurs. During assembly, converging continents produce collisional origins along the sutures that join them. During breakup, extensional tectonics can thin the crust and produce rift-related uplift that later become sites of renewed collision. In this way, the scars of past collisions can influence the geography of future ones. The legacy of ancient mountain building is visible in the continental crust today. Many cratons are bordered by belts of deformed and metamorphosed rock that mark the sutures of past origins. These belts may contain fragments of oceanic crust preserved as ophiolites, slivers of mantle peridotite, and exotic terrains carried in from far-travelled plates. Geologists trace these features across continents to reconstruct the configuration of ancient landmasses and the sequence of events that brought them together. Over deep time, the mountains themselves vanish, but the evidence of their making remains, locked in the structures, minerals, and geochemistry of the rocks. From the planetary perspective, mountain belts are temporary expressions of deeper, longer-lived processes. The movement of plates, the cycling of crust between surface and mantle, and the slow release of heat from the planet's interior. The surface form is transient, but the tectonic patterns that produce it are persistent, reappearing in different places and at different scales throughout Earth's history. Seen in this way, the rise of a mountain range is less a singular event than part of a continuous rhythm. Its peaks the crests of waves in a sea of stone. The stillness we see in an eroded range is simply another stage in that rhythm, as certain in its continuation as the next collision that will raise new peaks elsewhere, along the edges of subduction zones, where oceanic lithosphere sinks into the mantle. Volcanic arcs take form, tracing graceful curves above the descending slab. These arcs may rise from the sea as chains of islands, or stand as mountain belts on continental margins, but their origins lie deep in the mantle wedge above the subducting plate. As the slab descends, it carries with it water locked within minerals of the oceanic crust and overlying sediments. Increasing pressure and temperature force the release of these volatiles, which percolate upward into the overlying mantle. There, the addition of water lowers the solidus, allowing partial melting of the peridotite. The resulting magmas are less dense than the surrounding rock, so they ascend slowly through the mantle and crust, sometimes pooling in magma chambers before erupting at the surface. The chemistry of arc magmas reflects both their mantle source and the contributions from the slab and sediments. Basaltic magmas may evolve to andesite or rhyolite through fractional crystallization, assimilation of crustal material, or mixing with other magmas. The erupted products range from fluid lava flows to explosive pyroclastic deposits, depending on composition, gas content, and water interaction. Over long timescales, these processes build substantial volcanic edifices, their slopes mantled with lava flows, ash, and debris. Between eruptions, weathering and erosion reshape the surface, carrying volcanic material downslope into surrounding basins. In continental arcs, magmatism is often accompanied by the intrusion of large plutons at depth, cooling slowly to form granitic batholiths that may one day be exposed by erosion. Island arcs, by contrast, are typically smaller and more isolated, but their growth is no less significant. Successive eruptions and intrusions can eventually build them into sizable land masses. One quiet irony is that volcanic arcs, often perceived as dangerous and unstable, are in geological terms constructive features, adding material to the crust over millions of years. Another irony is that while their eruptions can alter landscapes in hours, the arcs themselves require tens of millions of years to assemble. A third lies in their eventual fate. Many arcs are temporary, destined to be accreted to continents or consumed in future subduction, leaving only fragments in ancient mountain belts. The distribution of volcanic arcs is closely tied to plate tectonics. They form parallel to trenches, offset inland from the subduction zone by a distance determined by the angle and depth of slab descent. Steeper subduction produces arcs closer to the trench, while shallower angles shift them farther inland. In some cases, back arc basins develop between the arc and the continent or behind an island arc, opening as spreading centres form in response to trench rollback. These basins create new oceanic crust even as subduction destroys old crust nearby. A juxtaposition of constructive and destructive processes in close proximity. The life cycle of a volcanic arc is linked to the evolution of its subduction zone. Changes in the direction or rate of plate convergence can shift the position of the arc, alter its volcanic style, or shut it down entirely. Arc migration leaves behind belts of extinct volcanoes and plutonic rocks, which may later be deformed and metamorphosed during continental collision. These ancient arcs are preserved in orogenic belts, their distinctive rock assemblages, volcanic elastics, intrusive suites, and arc-derived sediments, acting as markers of past tectonic environments. Despite the clear link between subduction and arc magmatism, uncertainties remain about the details of magma generation. The relative contributions of slab-derived fluids, sediment melts, and mantle wedge material vary between arcs and over time. Geochemical analyses such as isotope ratios and trace element patterns provide clues. but the complexity of magma mixing and crustal contamination means that definitive answers are elusive. Seismic imaging reveals zones of partial melt beneath arcs, but the geometry and connectivity of these melt regions are still subjects of study. Volcanic arcs influence more than the solid Earth. Their eruptions inject gases such as water vapour, carbon dioxide and sulfur dioxide into the atmosphere, affecting climate and atmospheric chemistry. Over geological timescales, arc volcanism plays a role in the carbon cycle, releasing carbon stored in subducted sediments and crust, while also contributing to the drawdown of carbon dioxide through the weathering of volcanic rocks. The interaction between tectonics, volcanism, and climate is complex, with feedbacks operating over millions of years. The arcs also create habitats both on land and in the sea. Volcanic soils, rich in minerals, can be highly fertile once weathered, supporting diverse ecosystems. In the marine realm, hydrothermal vents near volcanic islands provide energy and nutrients to unique biological communities. These ecological effects are side products of tectonic processes, unplanned yet influential in the history of life. In their growth, arcs contribute to the assembly of continents. When an island arc collides with a continental margin, it may be accreted, welding its crust onto the larger landmass. Such accreted arcs are common in the geological record, identifiable by their arc volcanic and plutonic rocks, associated sedimentary sequences, and distinctive geochemical signatures. Over time, multiple arcs may be stitched together along a continental margin, building complex belts of mixed origin. The structure of a volcanic arc is layered from surface to depth. At the top are the volcanic products, lava flows, pyroclastic deposits, and volcanic lastics reworked by erosion. Beneath these lie shallow intrusions such as sills and dikes, feeding the surface eruptions. Deeper still are the large plutons that represent the frozen roots of ancient magma chambers. At the base, the arc crust transitions into the mantle wedge, where melting begins. This structure is often preserved when arcs are accreted to continents and later uplifted, allowing geologists to reconstruct the vertical profile of ancient arcs from exposed cross-sections. The interplay between volcanism and tectonics in arcs is a balance of forces. Magma supply depends on the rate of subduction and the thermal structure of the slab and mantle wedge. Eruption style is influenced by magma composition, volatile content, and crustal thickness. Arc longevity depends on the persistence of the subduction zone, which in turn is governed by the larger scale motions of the plates. When a subduction zone shuts down, perhaps because a continent has entered the trench or the plate boundary has shifted, the arc becomes extinct. Erosion strips away the volcanic peaks, rivers carry their debris to the sea, and the deep plutonic roots are slowly revealed. From the perspective of deep time, arcs are transient, their lifespans measured in tens of millions of years, but their contribution to continental growth and geochemical cycling is lasting. The quiet lesson of volcanic arcs is that they are both makers and markers. They build crust even as they signal the location of destruction beneath, and they persist in the geological record long after the processes that formed them have ceased. Their curved chains, visible on maps and from space, are momentary patterns in the restless crust, destined to shift, merge, or vanish in the continuing rearrangement of the planet's surface. Across the surface of the planet, ocean basins open and close in slow cycles, their birth and death recorded in the geometry of ridges, trenches, and passive margins. An ocean begins as a rift, where continental lithosphere stretches and thins under tension. Mantle upwelling fills the gap with basaltic magma, forming new oceanic crust that pushes the continents apart. Over millions of years, this seafloor spreads laterally from a mid-ocean ridge, carrying with it a pattern of magnetic stripes that record the history of field reversals. At first, the young basin is narrow, its margins steep and faulted, but as it widens, the flanks subside and are buried under sediments from the continents. Shallow continental shelves develop along passive margins, their broad expanses covered by sediments carried by rivers, wind, and ocean currents. These shelves become repositories for thick sequences of rock, recording not only the local environment but also the broader changes in sea level, climate, and sediment supply. The quiet irony of a passive margin is that while it appears tectonically calm, it is born from a violent rift and destined to one day be consumed in a convergent boundary. Another irony is that the ocean basins themselves, so vast and seemingly permanent, have lifespans shorter than many continental cratons. A third is that the older sediments on the seafloor are still young by geological standards, because older crust has been recycled into the mantle. As an ocean matures, its circulation patterns stabilize, distributing heat and nutrients across the basin. Currents are guided by the shapes of the continents, ridges and fracture zones, influencing climate both locally and globally. Over long intervals, the positions of continents and ocean gateways change, altering circulation and triggering shifts in climate regimes. For example, the opening of the Drake Passage between South America and Antarctica allowed the Antarctic circumpolar current to form, isolating Antarctica and promoting the growth of its ice sheet. Ocean basins also serve as sinks and sources in the carbon cycle. Carbonates precipitate from seawater and accumulate on the seafloor, while organic carbon is buried in sediments. Subduction zones return some of this carbon to the mantle, releasing it again through arc volcanism, completing a cycle that operates over millions of years. The closing of an ocean begins when subduction zones develop along its margins. As oceanic lithosphere is consumed, the continents on either side are drawn closer together. Volcanic arcs form along the active margins, and sediments from the passive margins are scraped off or folded into the growing orogenic belts. Eventually, the last of the oceanic crust between the continents is subducted, and the continents collide, producing mountain belts and suturing the once distant land masses together. The Iapetus Ocean, for example, opened in the early Paleozoic and closed within a few 100 million years, its destruction recorded in the Appalachian and Caledonian origins. The Wilson cycle describes this repeated opening and closing of ocean basins, a fundamental rhythm of plate tectonics. It begins with continental rifting, progresses to seafloor spreading and ocean basin development, and ends with convergence and collision. Each stage leaves distinct geological signatures: rift basalts and faulted crust, oceanic crust with magnetic anomalies, accretionary wedges and volcanic arcs, and collisional mountain belts with sutures marked by ophiolites and high-pressure metamorphic rocks. These signatures allow geologists to reconstruct the history of oceans that have long since vanished. Yet uncertainties remain about the initiation and evolution of ocean basins. The exact triggers for continental rifting are debated. Mantle plumes, far-field tectonic stresses, or a combination of both may be responsible. The factors controlling the lifespan of an ocean, whether it will close quickly or persist for hundreds of millions of years, depend on the evolving configuration of plates and mantle convection patterns. Modern oceans provide case studies for all stages of the cycle. The Red Sea represents an early-stage rift transitioning towards seafloor spreading. The Atlantic Ocean is a mature basin with broad passive margins. The Pacific Ocean is in a closing phase, ringed by subduction zones that are consuming its crust and gradually reducing its size. The geological and climatic consequences of ocean basin changes are far-reaching. When oceans close, continents collide, altering atmospheric and oceanic circulation and changing patterns of rainfall and temperature. Mountain building associated with collision can increase global weathering rates, drawing down carbon dioxide and influencing climate. Conversely, the opening of new oceans can create warm, shallow seas that promote carbonate deposition and affect biodiversity. Passive margins, though tectonically inactive, are dynamic environments shaped by sedimentation, subsidence, and sea level fluctuations. During high sea levels, shallow seas flood the margins, depositing carbonates and fine-grained sediments. During low sea levels, rivers extend across the shelves, cutting valleys and delivering coarse sediments to the slope and deep basin. These changes are preserved in sedimentary sequences, which can be used to interpret past sea level changes and climate variations. The stability of a passive margin can be disrupted by the initiation of subduction nearby. If a new convergent boundary forms, the once quiet margin can become an active margin, its sediments deformed and uplifted, its shelf truncated by erosion. Such transitions mark the end of the passive phase and the beginning of ocean closure. Ocean basins are also sites of significant resource accumulation. Passive margins often contain thick sequences of sediments rich in organic material, which can generate hydrocarbons under the right conditions. Active margins can host mineral deposits formed by hydrothermal activity, at spreading centers, or by magmatic processes in volcanic arcs. These resources are incidental outcomes of the tectonic processes that create and destroy oceans. From the planetary perspective, the opening and closing of ocean basins is a continuous process, with multiple basins at different stages of the Wilson cycle at any given time. The balance between spreading and subduction maintains the planet's surface area while constantly rearranging its geography. The stillness of the present-day map hides the motion that will one day erase current oceans and create new ones in their place. In this view, every shoreline is temporary, every sea a transient stage in the long rhythm of tectonics. The ocean's permanence exists only in its presence, not in its boundaries, for the basins we know are merely chapters in a story that began long before them and will continue long after they are gone. Rift valleys mark the places where continents begin to part. The lithosphere stretched and thinned until it fractures, creating long, narrow depressions bounded by steep fault scarps. The process starts quietly, often in regions of pre-existing weakness such as old suture zones or failed rifts, where the crust yields more readily to extensional stresses. Heat from the mantle rises toward the surface, sometimes focused by plumes, causing thermal expansion and gentle uplift over broad areas. As the crust is pulled apart, it fractures along normal faults, dropping central blocks relative to their flanks to form a graben. These valleys may initially hold rivers or lakes, their waters trapped between the high shoulders of the rift. Volcanism often accompanies rifting, as decompression melting in the mantle produces basaltic magma that ascends through faults and fissures. Lava flows spill across the valley floor, mingling with sediments carried in from the surrounding highlands. Over time, continued stretching deepens the rift, and the volcanic and sedimentary layers pile up, recording the alternating rhythms of eruption and erosion. The East African Rift today offers a glimpse of this process, with active volcanoes, deep lakes, and earthquake activity marking the slow separation of plates. In some cases, rifting progresses to the point where the continental crust is so thinned that it ruptures entirely, allowing oceanic crust to form. This transition creates a narrow seaway, as in the Red Sea, where new basaltic crust grows at a spreading centre between diverging continental margins. The margins that flank the rift eventually subside and become passive continental shelves, beginning the life of a new ocean basin. A quiet irony is that many rifts never reach this stage. Failed rifts, known as oligocesians, remain as scars within continents, often filled with thick sequences of sediments and lavas that tell of an aborted attempt at continental separation. Another irony is that the earliest signs of rifting, gentle uplift, scattered volcanic centres, can be subtle, escaping notice until faulting and subsidence make the process unmistakable. A third is that while rifting may take tens of millions of years to create an ocean, the initial break can occur in geological moments when stress exceeds the crust's strength. The geometry of a rift is often segmented, with offset basins linked by transfer faults. These segments may be active at different times, shifting the locus of extension along the rift zone. Magmatism varies as well, from abundant basaltic flows in volcanic rifts to more limited intrusions in amagmatic rifts. In some cases, the stretching is so intense that the crust becomes extremely thin, and blocks of lower crust or upper mantle are exhumed at the surface. Such hyperextended margins, later submerged beneath rising seas, preserve a record of extreme tectonic thinning and the transition from continental to oceanic crust. Sedimentation in rift valleys reflects both local and regional controls. In closed basins, sediments may be dominated by lacustrine deposits, mudstones, siltstones, and evaporites that record changes in lake level and chemistry. In open systems, river deltas prograde into the rift, delivering sand and mud that may be interbedded with volcanic ash and lava flows. These sediments can be rich in fossils, providing snapshots of life in rift environments, from fish and mollusks in lakes to mammals and birds on the surrounding plains. As rifting continues, magmatism may evolve, producing more silica-rich compositions through fractional crystallization or crustal assimilation. Large volcanic edifices can form along the rift margins, their eruptions blanketing wide areas with ash and lava. The interaction between volcanism and faulting can create complex landscapes, with volcanic cones aligned along fissures, lava-dammed lakes, and ash layers that serve as time markers within the sedimentary record. Eventually, if spreading begins, the locus of magmatism shifts to the new mid-ocean ridge, and the rift valley becomes the nascent ocean floor. The shoulders of the rift, uplifted during early extension, are gradually eroded, their sediments carried into the subsiding margins. These passive margins may remain stable for hundreds of millions of years, but the rift that formed them remains visible in the arrangement of faults, the thickness of sediments, and the composition of the underlying crust. Uncertainty about rifting centre on its initiation and progression. Some rifts seem to form above mantle plumes, where hot material rises and weakens the lithosphere from below. Others appear to result from far-field stresses transmitted from distant plate boundaries. The balance between these mechanisms and the role of inherited structures in localizing extension is still debated. Seismic imaging and drilling in modern rifts help clarify these processes, but the deep past offers only partial records, altered by later tectonism and erosion. The influence of rifting extends beyond the continents themselves. New oceans change global circulation, opening pathways for currents and altering climate. The breakup of supercontinents through rifting can redistribute landmasses across latitudes, affecting atmospheric circulation and the distribution of ecosystems. Rift valleys also concentrate resources. Sediments rich in organic material may generate hydrocarbons, while volcanic rocks may host mineral deposits formed from hydrothermal fluids. The legacy of a rift persists long after active extension ceases. Failed rifts may guide later tectonic activity, acting as zones of weakness during compression or renewed extension. Some become sites of later mountain building when continents collide, their earlier sedimentary fills folded and metamorphosed into complex belts. Others remain as lowlands, their flat floors and straight margins betraying their tectonic origin even after erosion has softened their edges. From the planetary perspective, rifting is a surface response to deeper currents in the mantle, a release of tension in the brittle outer shell as the ductile interior flows beneath. It is neither inherently destructive nor constructive, but a stage in the larger tectonic cycle that creates and destroys oceans, assembles and disperses continents. The stillness we see in ancient rift landscapes today is the quiet after motion, the pause before the next shift, the frozen trace of a process that, given enough time, will begin again elsewhere. Over spans of hundreds of millions of years, the continents follow a recurring pattern of convergence, assembly, and dispersal known as the supercontinent cycle, in which all major landmasses periodically gather into a single vast expanse before breaking apart again. The earliest known examples, such as Kearey and Columbia, are reconstructed from fragments whose geological and paleomagnetic records align across oceans, while more recent supercontinents like Rodinia, Pannotia, and Pangaea are documented in greater detail. Each cycle begins with the slow closing of ocean basins, driven by subduction that consumes the intervening seafloor and draws continents together. As collisions occur, sutures form, zones of deformed and metamorphosed rock marking where once separate plates fused into a single continental mass. These sutures often preserve ophiolites, the remnants of oceanic crust and mantle thrust onto the continents, and high-pressure metamorphic assemblages that testify to deep burial during convergence. Once assembled, a supercontinent dominates global tectonics, influencing mantle convection by acting as a massive insulating lid. Heat builds beneath its thick lithosphere, altering convection patterns and sometimes reorganizing plate boundaries at its edges. The interior of the supercontinent becomes tectonically quiet, its crust stable and resistant to deformation, while its margins may remain active with subduction and magmatism. Climate across such a large landmass varies widely. Interiors far from the sea are often arid, while coasts may be humid, and high-latitude regions can support ice sheets if global conditions are cool enough. Ocean circulation is disrupted, with currents forced to navigate around the supercontinent's edges, affecting heat distribution and atmospheric circulation patterns. This reorganization can influence global climate on timescales of tens of millions of years. The supercontinent phase does not last indefinitely. As mantle heat accumulates beneath it, regions of the lithosphere weaken, and upwellings, sometimes in the form of mantle plumes, begin to focus rifting. These plumes produce large igneous provinces, vast outpourings of basalt that may cover millions of square kilometers and inject significant volumes of gases into the atmosphere. Rifting initiates along zones of weakness, often reactivating old sutures or failed rifts. As extension progresses, the crust thins, fault-bounded basins form, and eventually new oceanic crust appears, splitting the supercontinent into separate plates. This marks the beginning of a new dispersal phase, with continents drifting apart and new ocean basins expanding between them. A quiet irony is that the very size and stability of a supercontinent, its ability to trap heat, sows the seeds of its own fragmentation. Another is that while supercontinents appear to be singular events, their formation is merely one stage in a repeating cycle, and their breakup ensures the eventual formation of the next. A third lies in the persistence of their fragments. Even after breakup, the sutures and cratonic cores survive, recognizable in geological patterns that span multiple cycles. The timing of the supercontinent cycle is a subject of ongoing study. Estimates vary, but many reconstructions suggest a period of roughly 500 to 700 million years between successive assemblies. This periodicity is not exact. Each cycle is shaped by unique configurations of plates, mantle convection patterns, and climatic conditions. There is debate about whether the cycle is an inevitable feature of plate tectonics or a contingent outcome of Earth's current mantle and lithosphere properties. Paleomagnetic data combined with geological correlations and fossil evidence are the primary tools for reconstructing past supercontinents. These records allow geologists to trace the latitudinal positions and relative motions of cratons through time. However, uncertainties increase the further back the record extends, as rocks are altered, eroded, or buried by younger events. In some cases, only isolated fragments of sutures remain, making it challenging to confirm whether a proposed configuration truly existed. The supercontinent cycle has far-reaching consequences beyond tectonics. The assembly of a supercontinent can increase global mountain building, raising large orogenic belts that influence erosion rates and sediment supply to surrounding basins. Increased weathering of silicate rocks during such times can draw down atmospheric carbon dioxide, potentially leading to cooling and even global glaciations. Conversely, the breakup phase can promote warmer climates by increasing volcanic outgassing and creating more shallow continental shelves, which absorb and store heat differently than deep oceans. Life responds to these changes as well. The assembly of a supercontinent can reduce the number of coastal habitats and fragment ecosystems, influencing biodiversity patterns. Breakup, on the other hand, can create new coastlines and shallow seas, fostering diversification. The fossil record shows pulses of speciation and extinction that align broadly with phases of the supercontinent cycle. Though the relationships are complex and influenced by multiple factors, the persistence of continental cores across cycles means that some cratons have participated in multiple assemblies, their rocks preserving evidence of collisions separated by billions of years. These ancient terrains are geological archives, containing minerals like zircon that can be precisely dated and isotopically analyzed to reveal the timing and conditions of past tectonic events. Some zircons are older than 4 billion years, surviving through repeated cycles of burial, metamorphism, and erosion, silent witnesses to the planet's earliest crustal history. The breakup of a supercontinent is not a single event, but a drawn-out process that may span over 100 million years. Initial rifting is localized, and fragments may drift only slowly before new spreading centers accelerate separation. In some cases, microcontinents or island arcs are caught between diverging plates, creating complex patterns of collision and accretion that continue long after the main breakup. Ocean basins formed during dispersal evolve through their own Wilson cycles, eventually closing to form the next supercontinent. From the planetary perspective, the supercontinent cycle is a deep rhythm of surface change, one that integrates the motion of plates, the flow of the mantle, and the long-term evolution of the atmosphere and oceans. Its tempo is slow enough that no single species could witness a full cycle, yet its effects shape the face of the planet in ways that endure across eons. The stillness we perceive in modern continental arrangements is simply a pause between movements, a midpoint in a cycle that has repeated for most of Earth's history, and will likely continue for as long as plate tectonics endures. Beneath the forests, cities and seas of the present day, the boundaries between tectonic plates lie hidden in plain sight, their positions marked only by subtle shifts in geology, topography, or seismicity. These boundaries are of three main types: divergent, convergent, and transform, each with its own signature processes and structures, yet all part of the continuous network that encircles the planet like the seams of a living shell. Divergent boundaries are the sites of crustal creation, where plates move apart and mantle upwelling generates new lithosphere. Most lie along mid-ocean ridges, concealed beneath thousands of meters of water, but some occur on land as rifts, such as the East African Rift, where continents are slowly splitting. Convergent boundaries are the zones of destruction, where one plate descends beneath another in subduction zones, or where two continents collide, crumpling their edges into mountains. Transform boundaries are the connectors, accommodating lateral motion as plates slide past one another along strike-slip faults like California's San Andreas or New Zealand's Alpine Fault. These boundaries are rarely sharp lines. Rather, they are zones several kilometers to hundreds of kilometers wide, within which strain is distributed across multiple faults and deformation features. A quiet irony is that while plate boundaries are the most active tectonic environments on Earth, many remain unmapped in detail because they are buried beneath ocean or sediment. Another irony is that transform boundaries, which have little vertical motion and no volcanic arcs, can still produce earthquakes large enough to reshape landscapes in moments. A third is that some boundaries persist for hundreds of millions of years, long after the forces that created them have shifted elsewhere, acting as lines of weakness that may be reactivated in future tectonic episodes. Along divergent boundaries at mid-ocean ridges, the steady addition of new crust pushes plates apart at rates from a few millimeters to more than 10 centimeters per year. The ridge axis is segmented by transform faults, which offset the spreading centers and produce small earthquakes as the plates adjust their relative motions. The youngest crust lies at the ridge crest, cooling and subsiding as it moves away, accumulating sediment over tens of millions of years until it is eventually recycled at a trench. Convergent boundaries vary in expression depending on the nature of the colliding plates. Ocean-continent convergence produces deep-sea trenches, volcanic arcs, and forearc basins. Ocean-ocean convergence creates island arcs. Continent-continent convergence results in high mountain belts and thickened crust without significant subduction. The seismicity of convergent margins extends from shallow earthquakes near the trench to deep focus events tracing the descending slab into the mantle. Transform boundaries accommodate horizontal displacement without significant creation or destruction of crust. They can connect segments of mid-ocean ridges, link subduction zones, or cut across continents. Their motion is typically localized along major faults, but secondary faults and distributed deformation often occur in surrounding regions. Over geological time, the location of plate boundaries shifts as plates change direction, split, or merge. When a spreading center shuts down, its divergent boundary disappears, leaving behind a fossil ridge now part of a single plate. When subduction consumes the oceanic crust between two continents, the convergent boundary is replaced by a collisional origin, and active deformation gradually wanes. Transform boundaries can become inactive if plate motions change so that the relative movement across them ceases. The reactivation of ancient boundaries is a recurring theme in tectonics. Old suture zones, rifts and faults often serve as the sites of new plate boundaries because their crust and lithosphere are already weakened. This inheritance shapes the geometry of future plate configurations, creating patterns that echo through multiple supercontinent cycles. Uncertainties remain in the exact mapping of plate boundaries, especially beneath oceans and ice sheets. Seafloor mapping, seismic surveys, and satellite geodesy have greatly improved the precision of boundary locations, but gaps persist in remote areas. The depth and nature of the plate interface in subduction zones are also subjects of study, with implications for understanding the generation of large earthquakes and tsunamis. Some plate boundaries are diffuse, spanning broad zones where the lithosphere is fragmented into small blocks separated by numerous faults, as in the Western Pacific or parts of East Africa. These regions challenge the classical view of rigid plates and highlight the complexity of plate interactions. Plate boundaries are also the primary sites of energy release in the form of earthquakes and volcanic eruptions. The largest earthquakes occur at subduction zones, where decades or centuries of strain are released in minutes. Volcanism at boundaries not only builds mountains and islands, but also contributes to the long-term cycling of elements between Earth's interior and surface. Hydrothermal systems at mid-ocean ridges, driven by magmatic heat, alter the oceanic crust and influence seawater chemistry, while arc volcanism releases gases that interact with the atmosphere and hydrosphere. Over millions of years, the activity at plate boundaries reshapes continents and ocean basins. New crust added at divergent boundaries balances the crust consumed at convergent boundaries, maintaining the planet's surface area. The arrangement of these boundaries determines the motion of plates, the location of mountains and trenches, and the distribution of earthquakes and volcanoes. From the planetary perspective, plate boundaries are the moving joints of a dynamic shell, transferring momentum and heat between Earth's deep interior and its surface. They are transient in location but permanent in function, essential to the tectonic system that has shaped the planet for billions of years. The stillness we perceive in the landscape masks the motion occurring along these boundaries, a motion so slow that it requires patience measured in geological time to see. Yet in that stillness lies the potential for sudden change, for boundaries can shift, break, and reform in ways that alter the face of the Earth in both quiet increments and abrupt events. In the deep view, each fault, trench, ridge, and transform is a thread in a seamless web. Its position today only one frame in the long film of the planet's shifting skin. Even now, the plates continue their slow drift across the planet's surface, carried by the deep currents of mantle convection and driven by the combined forces of slab pull, ridge push, and gravitational spreading. The movement is so gradual, mere centimeters per year, that a lifetime passes without perceptible change. Yet over millions of years it rearranges continents, reshapes oceans, and alters the climate and biosphere. In the present configuration, the Pacific plate is shrinking as subduction zones consume its edges, while the Atlantic Ocean widens along the mid-Atlantic ridge. The Indian plate pushes into Eurasia, sustaining the uplift of the Himalaya, and the African plate is slowly rifting apart along the East African rift system. These motions are tracked with precision by satellite geodesy, which measures the positions of fixed points on Earth's surface to millimeter accuracy, confirming that the plates move as predicted by plate tectonic theory. Yet the forces driving them are not uniform in strength or effect. Slab pull, the gravitational force exerted by a sinking slab of cold, dense oceanic lithosphere, is considered the dominant driver, but ridge push from the elevated crests of spreading centers and basal drag from mantle flow beneath the plates contribute as well. The relative importance of these forces varies between plates and over time, depending on boundary geometry, mantle temperature, and the age and density of the lithosphere. A quiet irony is that the fastest moving plates are often those being consumed most rapidly, as in the case of the Pacific plate, which is drawn into surrounding trenches on nearly all sides. Another is that the largest plates can be the most geologically diverse, containing both active margins with high seismicity and volcanic activity, and passive margins that have been quiet for hundreds of millions of years. A third lies in the persistence of motion itself. While continents and oceans change places, the cycle of creation and destruction continues without pause, never allowing the surface to reach a fixed final state. Modern tectonic activity can be placed within the context of the supercontinent cycle, with some researchers suggesting that the current arrangement of plates is partway through a dispersal phase that will eventually lead to the assembly of a new supercontinent, sometimes called Amasia or Pangaea Proxima, or Arce. If present trends continue, the Pacific could close entirely within the next 200 to 300 million years, bringing the Americas into collision with Asia, while the widening Atlantic might one day begin to narrow as subduction zones form along its margins. The exact configuration of the next supercontinent is uncertain, dependent on evolving mantle convection patterns and the initiation of new plate boundaries. While the grand scale of tectonic motion is measured in millions of years, its effects can be immediate and catastrophic on human timescales. Subduction zones produce the largest earthquakes and tsunamis, transform faults, generate destructive shallow quakes, and volcanic arcs periodically erupt with enough force to alter climate. Yet even these events are brief flashes within the long, steady rhythm of plate motion, which over time smooths and reconfigures the scars it creates. The geological record shows that the fundamental processes of plate tectonics have been operating for at least 3 billion years, though the details of their style and speed in the early Earth remain debated. Higher mantle temperatures in the Archean may have driven faster convection and smaller plates, with more frequent overturning of the lithosphere. As the planet cooled, plates grew larger and their motion slowed, but the essential cycle of creation, movement, and destruction persisted. This continuity suggests that plate tectonics is not merely a phase in Earth's history, but an intrinsic mode of planetary heat loss, one that will continue as long as the mantle remains sufficiently convective and the lithosphere strong enough to break into plates. Uncertainties about the future include how long plate tectonics can persist. Over billions of years, as the planet continues to cool, the mantle's ability to sustain vigorous convection will diminish. The lithosphere may grow thicker and stronger, making it harder for new subduction zones to initiate. In such a scenario, Earth might eventually transition to a stagnant lid regime like that seen on Venus, with a single rigid shell overlying a convecting mantle. But for the foreseeable geological future, the signs of active plate tectonics, mid-ocean ridges, subduction zones, transform faults, remain abundant. From a planetary systems perspective, the movement of tectonic plates is a coupling between deep and surface processes. It links the flow of the mantle to the shape of the continents, the chemistry of the oceans, and the composition of the atmosphere. Volcanism at plate boundaries releases gases and minerals that influence climate and provide nutrients for ecosystems, while weathering of uplifted rocks draws down carbon dioxide, feeding back into the climate system. The arrangement of continents affects ocean circulation, which in turn influences climate and patterns of biodiversity. Life itself both adapts to and modifies the products of plate motion, colonizing new habitats created by uplift or rifting, and altering the chemical environment through processes like photosynthesis and respiration. The present-day map, with its arrangement of continents and oceans, is simply one frame in a long sequence of tectonic configurations. Future reconstructions will show entirely different patterns, with familiar landmasses joined or separated, mountains eroded and replaced by new ranges, and ocean basins shifted or erased. The geological features we regard as permanent, coastlines, mountain belts, island chains, are all transient expressions of a deeper, ongoing process. From the human vantage point, plate tectonics offers both a source of hazards and a framework for understanding the planet's long history. The slow pace of motion belies its transformative power, for given enough time, it can close oceans, lift continents to the height of the sky, and bury them again beneath the sea. The stillness of the present is only an illusion born of our brief perspective, for beneath the surface the plates never rest, their motion as constant as the flow of the mantle below, In this restless stillness lies the enduring character of Earth's lithosphere, to move without haste, to change without end, and to carry forward the geological story into whatever form the next chapter will take. Now the rhythm slows, the forward motion easing until it is barely perceptible, the vast machinery of crust and mantle becoming a background hum. The plates still move, but in this moment they seem fixed, the continents settled in their present arrangement, oceans holding their shapes as if they had always been this way. Mountains stand in the cool air, rivers trace their slow paths to the sea, trenches lie quiet beneath their weight of water. Heat still rises from the mantle, ridges still breathe new crust into being, and subduction zones still draw the old crust down, yet here at the surface there is only the stillness of landscapes that have learned patience. In the deep ocean the mid-ocean ridges stretch unseen, their volcanic ridges no louder than the beat of the planet's own heart, while far away the trenches yawn silently, their descent into darkness marked only by the slow drift of marine snow. Above them, waves cross without knowledge of the stone below, wind moves across the water and clouds gather and break. On the continents, the ancient cratons rest in the quiet of their long survival, carrying the memory of supercontinents past and the certainty of those yet to come. Old mountain belts lie worn and subdued, their sharp edges long ago carried away as sand, their folded rocks speaking softly of collisions that ended hundreds of millions of years ago. Valleys curve gently between them, and forests or deserts fill the space where oceans once lay. Time here has no urgency. Each grain of sand, each ripple in a lake, each slow movement of groundwater through stone is part of the same long cycle, one in which the surface is shaped not by haste but by the balance between uplift and erosion, between creation and return. In this drawn-out quiet, the lines between what is changing and what endures blur. A coastline today may outlast a species but vanish before the next supercontinent gathers. The present is only one configuration among countless others, and the planet will not keep it for sentiment. Yet in its passing lies no loss, only the continuation of a story without a final page. The stillness deepens until it is the stillness of stone itself, the kind that underlies oceans and continents alike, untroubled by the small motions on its surface. It is here, in this quiet, that the mind can rest alongside the planet, carried neither forward nor back, but simply held in the enduring balance of its restless stillness.